has no classical analog and it is used as a resource in computational and communicational purposes. Some of the applications are in quantum teleportation, quantum cryptography, and quantum computing. So my work is based on bipartite entanglement. So in a bipartite quantum system, it is composed of two parties, which is described by vectors in the tensor product of two spaces, HA tensor HB. And this is how we describe a pure state in a Hilbert space. Mixture of pure states is called a mixed state. So if rho is a density matrix for a composite system, rho is a product state. If it can be written in the tensor product form, where rho A is the state for Alice and rho B is the state for Bob. And a state is called separable if it can be written as the convex combination of the product states. Otherwise, the state is entangled. There is another class of states which is classified on the basis of the property of distillation. So the free entangled states are called distillable states and the bound entangled states are called non-distillable states. Distillation is the procedure of converting a mixed state entanglement into the singlet form. Bound entangled states require entanglement for their creation, but entanglement cannot be distilled from them again. Originally, bound entangled states were considered not very useful in quantum information processing tasks, but later it is established as a valid resource, and some of the applications of bound entangled states are in quantum key distribution, entanglement activation, metrology, non-locality, and the non-distillability feature has also been linked to the irreversibility in thermodynamics. So entanglement detection problem is one of the most important problem in quantum information theory, and this gives a strong motivation to classify and detect entangled states. So a criteria to decide whether a given state is entangled or not is of high importance, and there are numerous criteria available in the literature to detect entanglement. Some of the criteria are given here: the positive partial transposition criteria, CCNR criteria, range criteria, covariance matrix criteria, and also some approaches through the construction of witness operator. So first let's talk about the PPT criteria, which is one of the most prominent criteria. So if we have a matrix A which is an n cross n block matrix with each block of size k, then partial transpose is described as the transpose of each block in the matrix. For example, in a 2-qubit state, which is given by the density matrix rho, rho TB, which denotes the partial transposition with respect to subsystem V, is defined like this, where transpose of each block is taken. So a matrix is said to be PPT or positive partial transpose matrix if its partial transposition has no negative eigenvalues. That means the A tau, which denotes the partially transposed matrix, it is a positive semi-definite matrix. So PPT criteria or Perez-Horodoky criteria states that if a bipartite state is separable, then it is PPT. That means it has positive partial transpose. So if we have a matrix A, so if that means the converse also holds only for 2-qubit and which denotes the system. If a state is separable, then it has positive partial transpose, and if there is a state is PPT, then it is separable. So in higher dimensions, there exist states which are PPT and they are not separable, they are entangled. So these states are called PPT entangled states or bound entangled states. And if the partial transposition is negative, then the state is entangled and it is called NPTES or NPT entangled state. So the partial transposition criteria cannot detect bound entangled states or PPT entangled states because it is a necessary sufficient condition only in two qubit and qubit qubit systems. So we have another criteria which is realignment criteria. This criteria is based on the realignment operation, and this criteria can detect bound entangled states. So let's define the realignment operation. So here the density matrix rho AB is given and the realigned matrix is given as the change of this index. It is also based on the permutation of matrix elements like the partial transposition criteria, but the permutation is different here. Uh, this is a density matrix rho, and we can see that the each block is written in the form of row. So it is based on row vectorization or column vectorization. So this criteria states that if a state is separable, then the trace norm of the realigned matrix is less than equal to 1. And if the trace norm of the realigned matrix is greater than 1, then we say that the state is entangled. So now the realignment criteria and partial transposition criteria, both the criteria are can detect entanglement. There are some NPT entangled states which cannot be detected by realignment criteria, but it can detect bound entangled states. So these two criteria work independently. So these criteria are based on index permutation. So this, which is an unphysical operation, so these cannot be realized experimentally. And the CCNR criteria or realignment criteria is based on the singular value decomposition, because uh, to ca- uh, to apply the criteria, one has to calculate the trace norm. So measurement of trace norm usually require full state tomography, which is resource consuming. So we need more operational criteria that are experimentally friendly or feasible. So recently there are some works which are based on the moments of the matrix, and it has been shown that the moments of the matrix carry much information about the states and they are relatively easy to measure. Some of the references are given here where the calculation of moments is given, how moments can be calculated and how it can be done in the experiments. So there are some protocols which are based on PPT moments or PT moments. So moment based PPT criteria and moment based CCNR criteria have been proposed, and it has been shown that they can be realized using a single copy qubit wise measurements and randomized measurement techniques, and also using the swap operators. So these are a few moment based criteria based on partial moments. So partial moment is defined as, if tau denotes the partial transposition, then the kth partial moment is defined as trace of rho tau to the power k. And the criteria says that if a state, any state satisfies this inequality, sorry, the criteria states that if rho is a PPT state, then it satisfies this inequality, and if this inequality is violated, then it is an NPT state. So these inequalities given by Albin involves three moments. So P1, P2, and P3, three moments of the partially transposed matrix are involved, and this criteria can detect entangled states. Another criteria was given in the form of D3 inequalities, DK inequalities, where the smallest one is D3 inequalities, which is given in equation number 7. And again, it holds for all PPT states, and if it is violated, then the state is entangled. So a more optimal criteria was given again in the form of an inequality, which holds for which is dependent on this positive map lambda, and it holds for all PPT states. Now these inequalities also, since they are based on the partial transposition criteria, they can detect only se- the sep- um, the NPT states, not the bound entangled states. So for bound entangled states, there to detect bound entangled states, there is a criteria which was recently given by Zhang, which is based on realignment moments. So this criteria defined realignment moments like this. So it is defined that rho R here denotes the matrix obtained after applying the realignment operation to the density matrix rho, and we take the rho r dagger and take the trace to the power k by 2. So this is how the kth moment of a realignment matrix is defined in this paper, and the separability criteria is given in the form of an inequality, which again involves up to third order moments. So we are giving another criteria which is based on the moments of the realignment matrix, and we have compared our, since our criteria can detect bounded angle states also, so we have compared the effectiveness of that criteria with this criteria. So let us see how the realigned moments or R moments is defined in our work. So if rho is a density matrix that represents n cross n state, then the first step that we have used is to find the characteristic equation of the operator rho r dagger rho r. So we have considered the operator rho r dagger rho r, which is n square cross n square Hermitian operator, and the characteristic equation is given as in equation 11, where d1 d2 dn square are the coefficients. Now using the Newton polynomials, these coefficients can be written in the form of the moments of the matrix rho r dagger rho r like this, and tk equal to trace of rho r dagger rho r to the power k is how we define the kth realigned moment of the matrix rho r dagger rho r. Now we use these moments to give a criteria which can detect entanglement. So first, we write the coefficients in the form of the singular values like this. It can be expressible in the form of the singular values. So the coefficients written in the terms of the first moment, d1 can be written as minus of t1, d2 can be written as half of t1 square minus t2. Similarly, the last coefficient is given by the determinant of the rho r dagger rho. And it can also be written in the form of the moments using the formula given here. Now the separability criteria based on R moments is given like this, that if a state is if rho is a bipartite state, M cross n bipartite state, and it has k non-zero singular values, and rho r has k non-zero singular values, that means the rank of rho r is k, denoted by sigma 1, sigma 2, sigma k. Then if the state is separable, the the inequality given in equation 20 holds. So that means k minus 1 dk to the power 1 by k plus t1 minus 1 is less than equal to 0. And if this inequality is violated, then we say that the state is entangled. Here t1 is the first moment, trace of rho r dagger rho r, and dk is product of the k singular values, which can be expressed in the form of the moments given in the formula here. So now we have given some examples where to check whether it can detect bound entangled states or NPT entangled states, and this is a tensor 4 bound entangled state, which is bound entangled or PPT entangled when Q naught is when P and Q equal to P naught and Q naught. So at one point this is PPT entangled, and for other P and Q it is an NPT entangled state. So this is the degenerated characteristic equation for this matrix, for the matrix rho r dagger rho r, and DIs are already defined. This is the expression for D8, and we found that the left hand side of the inequality is violated, so this is greater than 0. That means the state rho p naught q naught is detected by our criteria, and it can be concluded that it is PPT entangled. So we compared this with the Zhang's criteria based on realignment moments, and we found that it cannot detect this bound entangled state. And also the partial moments criteria, since they are not applicable only for the NPT entangled state, they cannot detect this state. So next we check the other NPT states, whether how efficient is this criteria can detect NPT states or not. So we found that the in this particular range, our criteria, which is based on the R moment criteria, it detects comparatively in a larger range as compared to the T3 criteria. Next is one NPT entangled states, 3x3 NPT entangled states with state parameter A. And here we find that all the criteria, the criteria given, the P3 PPT criteria given by Albin, D3 criteria given by Navin, and the P3 OPPT criteria, L1, L3, and L1, L2, and L3 represent those three criteria, and we find that our criteria can detect this entangled state in the whole family, since R1 is greater than 0, and since L1, L2, and L3, these inequalities are not violated, these are less than 0. These criteria cannot detect the state in the whole range. So to conclude, we have given a separability criteria for detecting entanglement in arbitrary dimensional bipartite states, and it is based on the partial information of the density matrix, and we have employed the
These are less
technique of
than 0.
realignment moments.
These criteria
Our
cannot
approach
detect the
can
state in
detect both PPT and NPT entangled states using low order moments of the realignment matrix. Also, the R moment criteria is able to detect certain NPT entangled states that were undetected by the partial moment based criteria. And we have proved we have proved in the paper that the non full rank realignment matrix of 2 qubit, that the non full rank realignment matrix in 2 qubit entangled state does not exist. So that means the last coefficient D4 is non-zero, and we have developed so if this is non-zero, then all the moments T1, T2, T3, and T4 will be employed to calculate the inequality, and for that much information will be needed. So we have given another criteria, especially for 2x2 systems, which is based on 3 moments T1, T2, and T3, and we have shown that that can also detect entanglement using less number of moments using that criteria. All about for me. Thank you all.
Thank you, Shruti, for this wonderful talk. Now, session is open for the question and answers. So, anyone have the question, then ask. We have the time.
Thank you for your talk. I have few questions. So, what steps are required to perform and then compute entanglement in case of Bell states by using your R moment criteria?
So for Bell states also, like this criteria is applicable to any state, to any bipartite state. So first we have to if it is an M cross, it is, let's say, in a 2 qubit state, first we have to calculate these moments T1, T2, and T. So let me just show the inequality. So this is the inequality. So for this we need the moments T1, T2, and T3, and T4, and apply this in the inequality. If the inequality is violated, then we say that the state is invalid.
And what is the meaning of moment? So could you please explain?
Okay, so moment means that if we have a matrix A and we take the trace of the matrix, then let's say we call it the first moment. So if we square the matrix A square and then we take the trace, it is called the second moment. If we take the cube of the matrix and then we take the trace, then it is called the third moment. and so on. So this is how we define the moment.
Mhm.
So
Okay.
let,
So
for example, this is partial moment. So the kth moment is defined as trace of this matrix rho tau to the power k.
mhm. Thank you. In case of continuous variables, can I apply the same?
In case of, I have no idea in case of continuous variables.
Mhm,
This this is applicable only to the discrete.
mhm. So also, can I apply to multipartite? I think only bipartite system, right?
Yeah, this is given for bipartite system, but there is a work by Liu et al. Where it is given for multipartite systems. Some kind of moment-based criteria is given for multipartite systems also. So you can check that. It is based on a permutation method. Like these are realigned moments or partial moments. So it is based on a general based on any kind of permutation. So you can refer to that paper. This P.
Mhm.
Liu in PRL.
So did you find some differences with other uh, criteria for entanglement, like Schmidt parameter? So are there any differences, or what new things we can do by using your criteria proposed by you? So,
So we
I
have
mean,
not, I mean, you are, so we have not, we have compared with, right now we have compared with the moment-based criteria. So
mhm,
the, if we apply the PPT criteria or realignment criteria, they will detect obviously more, they will be more efficient analytically, they will detect more entangled states. But from an experimental point of view, since moment-based criteria, it has been shown experimentally, there are some papers where it has been shown that they can, they are more feasible experimentally. So that is why we are giving a criteria based on realignment moments, and we have not compared with any other criteria, the
hmm.
efficiency part.
Okay, so moments, you mean mean values, mean number of photons I can, this is the first moment, the second moment is variances. So do you, I mean, propose, or do we have association with moments like these moments, right? Mean
Yes,
value number of photons.
yes,
Okay.
yes.
So,
Trace row square, and so on.
okay, okay. Now it's clear. So it is like a characteristic function in quantum optics we use to identify first type moment, second moment, and so on.
Yes,
Mhm. Thank you.
welcome.
So how many moments do I need to identify whether my state is uh, entangled or not?
Uh, to check whether the state is entangled, we have to apply this inequality, and this inequality is based on the rank of the realignment matrix. So if the rank of the realignment matrix is k, then we need k number of moments.
Mhm.
For example, in this example, this lambda to the power 8 plus the characteristic equation is given here. So this is a 16 cross 6. This will be a 16 cross 16 matrix rho r, and the number of moments that we require are 8 moments.
Hmm. Above then variances, I don't know how to in practice measure those moments. So okay. So do you also propose how to measure moments more than 2 of degree 2?
We have not proposed how to measure moments, but there are some references that you can refer, which are given here. So there is a paper by Sugato Bose where how we can calculate the moments using swap operators. higher order moments also. Like for NEK, it is given here, the protocol is given. So it is based on some machine learning techniques, and also there are papers by Alban and Neven where calculation of moments using the randomized measurement techniques is given.
Mhm. Okay, thank you. Is your work is already published or
This is on archive.
it's on archive still? Mhm,
So archive number is given here.
mhm, mhm,
This is available on archive.
mhm. So if I have some questions, then I can reach to you. Okay. Yeah,
Yes, you can
thank
reach.
you. Mhm.
Okay. Thank you, Shruti.
Thank you all.
So now you can share your slides.
Yeah.
We will move to our next speaker. Hi, Konikar, are you there?
Yes, hello.
You are audible. Now you can check also your video.
Yes.
Yes. Okay. You can start by sharing your screen.
Is it visible?
Yes, yes.
Okay. So may I start?
Okay. So let me introduce you. So our this speaker is Konikar Sen. She is from the HRI. She will be talking today about the compatible measurements. Konikar Sen, now you can start.
Yes. Thank you for giving me the opportunity to present my work here. The title of my talk is Can Incompatible Measurements Provide Advantage in Local State Discrimination? So the one word answer to this question is yes, incompatible measurements do provide advantage. But I'm not going to leave you by giving this just one word answer. So in this talk, I will discuss about which type of state discrimination tasks I'm talking about and which type of advantage or what amount of advantage you can get.